Today is a problem-solving session focusing on topic number 5 in our semester. Topic number 5 is permutations and permutation groups. As we've been talking about in class, permutations are going to give us a way of really encapsulating all the behavior that we can possibly see in finite groups can be observed somewhere inside of a subgroup of a permutation group, a subgroup of a symmetric group of a sufficient order. And that's kind of good news because the phenomena that we're studying here are phenomena that really give us a window into how all different finite groups can behave in some sense. But we're not going to focus on permutation groups from that perspective as much in this chapter. We had a chance to at least experience what Cayley's theorem is in our videos, but we're not really going to go much further than that as far as the link between symmetric groups and other finite groups, at least for right now. What I'm hoping we can most get out of this chapter is an understanding just of how the permutation groups operate. What are some of the important things to know about the orders of those groups and the orders of elements within those groups? What are some important things to know about particular subgroups inside of Sn? Because the ways that we investigate these kinds of questions are going to parallel the ways that we investigate similar questions as we move on throughout the semester. Some permutation groups are also kind of our last example of a new type of group that we're going to wrestle with this semester. Once we move forward into topic number 6, our interest is really going to be in building some more tools to compare groups one to another. And so in our chapter 6, we're finally going to get a chance to answer the question, what does it really mean rigorously for two groups to be the same? And so we'll build the concept of what's called an isomorphism, a function between groups that preserves their structure and which is invertible. But that's where we're shifting next. For this week, I've selected some problems that kind of run the gamut that we're going to work together on. From the really practical nuts and bolts minded problems down to the more generalizable and more abstract questions that we can ask and answer about groups of permutations. So here's what I've got kind of on tap. The first is I want to talk nuts and bolts. And in particular, we're going to look at a problem where I just give you an anagram of the word auctioned into the word education, and we're going to turn that anagram into disjoint cycle notation for a permutation and then do some calculations with that permutation. We're also going to talk more about the orders of elements in a symmetric group. So I really like this example because this example is going to invite us to find elements of order 2 in S4, alpha and beta, such that their product, their composition, has several different possibilities for order. Order 1, order 2, order 3. And what this kind of does is it puts the lie to the idea that it's straightforward to understand what the order of a product of permutations, or indeed a product of elements in any finite group, is based on knowing the orders of the elements individually. So we'll talk more about element orders, and then likewise, picking up on a problem that we did in our daily work, we'll talk about the how to determine whether or not an element of a given order does or does not exist in a symmetric group like S10, or in the alternating subgroup of that group, which is A10. Then I want to talk more about subgroups of Sn, subgroups of the symmetric group. So I have a couple of proofs that I hope we can get to. One of them is that if I have any subgroup at all of a symmetric group Sn, then either that subgroup consists completely of even permutations, in other words, it resides completely within An, or the only other possibility is that exactly half of the elements of that subgroup are even and the other half are odd. So the only way to have a subgroup in Sn is either for the whole thing to be within An, or for exactly half of it to be within An. And then finally, if we get time, we'll take a look at the proposition that every symmetric group is center-free. In other words, the only permutation in Sn for n greater than or equal to 3, the only permutation that commutes with every other permutation in that group is the identity permutation. So there's kind of the lay of the land. If you're watching via Twitch this morning and you're not a part of my class, feel free to contribute questions into the Twitch chat if you like, and I'll try and respond to those. But if you are my student this semester and you're watching us live today, contribute your questions via our Slack Doctor's Office channel. I'll get those as we go along, and I'll try to respond to them as we do. So let's get started. And we'll start with our nuts and bolts. So I just want us to together take a look at, sorry, here we go. So I want to just take a look at doing computations in the symmetric group. So how does it work? From a nuts and bolts perspective, what I'm doing here is giving you a permutation, the permutation that turns the word auctioned into the word education. And in order to do calculations with this permutation, it's a part of the symmetric group S9. Probably the first thing that we want to do is we actually want to come up with disjoint cycle notation for this permutation. So to do that, I'm just going to recopy this, what I call stack notation, over here. So auctioned on the one hand, education on the other. And I'm just going to write the numbers of the positions above my letters here. So 1 through 9. So that I can keep straight the positions, 1 through 9, with the symbols, the letters A, U, C, T, etc., that this permutation is acting upon. Okay, so how are we going to come up with a disjoint cycle notation for this particular permutation? Well, as usual, what we'll do is take one of my symbols. Let's say I take the first symbol just to get my process started, and I ask the question, where does that first symbol end up after this permutation does its thing? And the letter A ends up starting in position 1 and ending up in position 5. So my cycle is going to start off 1, 5. And to continue my cycle, I have to ask the question, where does position 5 end up going? Position 5 is my letter I, so I'll go north here to I, and then figure out where that position ends up. My I ends up in position 7, so my cycle will continue with a 7. And the letter in position 7 originally is N. That ends up in position 9. The letter D from position 9 ends up in position 2. So we'll continue this with a 2. The letter in position 2 is a U. That ends up in position 3. The letter C in position 3 ends up in position 4. The letter T in position 4 ends up in position 6. The letter O in position 6 ends up in position 8. And the letter E from position 8 ends up in position 1. And that, therefore, completes my cycle. So it turns out, for this example, that just writing out, just figuring out disjoint cycle notation for the permutation that turns the word auctioned into the word education actually gives me a permutation that is already just a single cycle. It's a 9 cycle. That there is a way of seating the numbers 1 through 9 around a round table, such that representing this permutation is the same thing as just representing the effect of every one of those positions taking one step to its right, moving one space to its right along the table. So there is cycle notation for sigma. Let me get that recorded down on the page here, just because I'm probably going to want to make some more room on my screen to write other things here in a minute. So let me just write, this permutation was 1, 5, 7, 9, 2, 3, 4, 6, 8. There we go. So there's cycle notation for this permutation. So what I want to do with this next is I want to use that cycle notation to determine a couple of other things. I want to determine cycle notation for sigma squared. What happens if this permutation acts twice in succession? Or sigma inverse. Sigma inverse would be a permutation which turns education back to auctioned, right? If it acted on the word education, it would turn it into auctioned, doing the opposite of what this permutation did. Okay. So let's look at that question next. If I want to find sigma squared, what I would need to do is I would need to find a permutation that is the result of this sigma happening twice. Well, every time this cycle happens twice, or every time the cycle happens once, sorry, each one of these positions is taking one step to its right. So sigma squared would be the result of taking 2 steps to the right. So if I want cycle notation for sigma squared, I would take the position number 1 and figure out where does it go after sigma happens twice. After sigma happens twice, 1 is going to end up not at 5, but at 7. And in turn, 7 is going to end up taking 2 steps to its right and ending up at position 2. 2 is going to take 2 steps to its right, end up at position 4. 4 is going to take 2 steps to the right and land at position 8. And then 8 is going to take 2 steps to its right. But in its first step to the right, it's going to wrap back around to 1. So in the second step, 8 is going to go to 5. So there's where my cycle ends up wrapping around. 8 goes to 1, goes to 5. And then 5, in turn, is going to take 2 steps to its right and end up at 9. 9 is going to take 2 steps to its right and ending up at 3. 3 is going to take 2 steps to the right, ending up at 6. And 6 is going to take 2 steps to the right, but those 2 steps to the right are going to take me back to 1. And the fact that I land back at 1 means that my cycle has completed. So cycle notation for sigma squared is just going to be this turns out to be another 9 cycle. And if you think about why this is a 9 cycle again, maybe it shouldn't be too surprising. I have 9 positions that I need to cover, and I'm skipping them 2 at a time. And since 2 is relatively prime to 9, we know that counting by 2's, mod 9, is going to generate all 9 of those positions without repeating any one of them until we get back to the original. So I'm going to kind of write that observation down as a conjecture. And that conjecture is that if sigma is a, let's say, a k cycle, then sigma to the n is a k cycle, provided n and k are relatively prime. So provided the GCD of n with k is equal to 1. So in this example, k was 9, we had a 9 cycle. N was 2, we were looking for the second power. And precisely because we find that 2 cycle just by counting by 2's in my cycle, and that counting happens mod 9 because I wrap around to the beginning once I get to the end, right? If I count by 2's mod 9, because 2 is a generator of z mod 9, precisely because 2 is relatively prime to 9, that shows that we get all the positions before we get back around to the original, which means we have a 9 cycle. So given that that is the way that it is, I actually want to do, I'm going to change our problem here a little bit so that when we get to the next part of this problem, instead of looking at the 5th power of sigma, because the 5th power of sigma, for the same reason that the 2nd power of sigma is a 9 cycle, the 5th power would have been as well. So I kind of think it's a more interesting question to look at the 3rd power, or maybe the 6th. Let's do the 6th. Just want to tweak that a little bit. Okay. So we figured out what sigma squared was. Let's figure out what sigma inverse would be. So sigma inverse is the permutation whose job is to do the opposite of what sigma does. So whatever sigma does, sigma inverse needs to undo. So how do we undo the permutation whose cycle notation is as shown here? 1, 5, 7, 9, 2, 3, 4, 6, 8. What is sigma inverse? Well, if sigma's job is to take steps to the right along this 9 cycle, or around a round table with 9 positions at it, sigma inverse's job should be to do the opposite, which is to take steps to the left around that same table. Right? So sigma inverse, we're going to find just by starting at position 1, because we always like to start at the lowest numbered position in any one of our cycles. That's just a convention. But then we're going to start by taking steps to the left instead of to the right. So I'm just going to read this cycle from right to left instead. When I take 1 step to the left of position 1, we're going to wrap around to 8. And so my cycle is going to go 1, 8. And then 8 is going to go to 6 when I take that step to the left. 6 is going to go to 4. 4 is going to go to 3, to 2, to 9, to 7, to 5. And then 5 is going to go back to 1, which means my cycle is complete. So there is cycle notation for the inverse of this permutation. Now let's move on to this next part of the question, which is to figure out what is the permutation sigma to the power 6. And then I want to use that permutation to act on the word education, just to get us some practice with what algebraists would call a group action on a set. Let's start by figuring out what is sigma to the power 6. So to figure out sigma to the power 6, I'm going to use that same principle that we used to figure out these other powers of sigma. I'm going to start with my position number 1, and then I'm going to take 6 steps to the right from position 1. But before I do that, let's make the observation that in a 9 cycle, or maybe I'll say it this way, in Z mod 9, going and adding 6 to a number is the same thing as subtracting 3 from that number. Right? Positive 6 and negative 3 are congruent mod 9. Another way to see that is taking 6 steps to the right around my table is the same thing as taking 3 steps to the left when I have 9 people seated around a table. 6 steps right equals 3 steps left. And in view of that, that would mean that the 6th power of sigma is the same thing as the minus 3rd power of sigma. If that helps us, because after all, the order of sigma is 9, because sigma is a 9 cycle. So sigma to the 9th is equal to the identity. And then just multiplying both sides of this equation by sigma to the minus 3 will show me sigma to the 6th is equal to sigma to the minus 3. Anyway, all of that is to say that the quick way of finding sigma to the 6th is by finding sigma to the minus 3, taking each of these positions and moving 3 steps to its left. So where is 1 going to go? It's going to take 1 step to the left over to 8, 2 steps to 6, 3rd step is going to land me at 4. So 1 is going to end up at 4 as we begin our cycle. What about 4? 3 steps to the left. Bling, bling, bling. 4 is going to end up at 9. And then 9, if I take 3 steps to the left, is going to go 7, 5, 1. And so since that goes around back to 1, we will close that cycle. But of course we're not done, because my permutation has not yet told me where 2 goes. 2 is the least numbered position that I haven't figured out yet. So we'll go from 2 and figure out 3 steps to the left. 1, 2, 3. 2 is going to go to 5. If I take 3 steps to the left from 5, it'll go 1, 8, 6. And then 3 steps to the left from 6 will get me back to 2, finishing that cycle. And the lowest numbered position we haven't figured out yet now is 3. 3 steps to the left from 3, which is, remember, the same as 6 to the right, is going to give me 7. And 3 steps to the left from 7 is going to put me at 8. And 3 steps to the left from 8 verifies that we've come back to 3, closing that cycle. And now we've accounted for all 9 of my positions. And this, therefore, is the 6th power of sigma for our cycle, for our 9-cycle sigma. So now let's take that information and act upon the word education with this particular permutation. So again, I'm going to come through and number my positions. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So, according to this first cycle, the symbol in position 1 is going to end up in position 4. So my E is going to end up in position number 4. So it's going to be underneath where we used to have a C here. So 1 is going to go to 4. And then my symbol from position 4, which is C, is going to end up in position 9. So I'll put my C down here in the 9th position. And the symbol from position 9, which is N, is going to end up back in position 1. So when 149 does its work, we're going to take the letters E, C, and N, and they're going to get permuted around in the way that I've indicated here. Let me try and keep track, just so that we can kind of see what we're doing. 149 had this effect. Right. It took the letters E, it took E and put it in position 4, and then C in position 9, and then N back in position 1. So there, 149 has done its job. Now we move forward to 256. For 256, we're going to start with my D in position 2 and put it in position 5. So D is going to end up here. And then the A from position 5 is going to go to position 6. And the T from position 6 is going to go back to position 2. So 256 has accomplished 2 goes to 5, 5 goes to 6, and 6 goes back to 2. Okay. So that now has done its business. Now we move forward to the last of our disjoint cycles, 3, 7, 8. In position 3 is a U. It's going to go to position 7, so I'll put the U right there in position 7 underneath my I. The I from position 7 is going to go to position 8. So we'll put this I here. And then the O from position 8 is going to go back to position 3. and now 3, 7, 8. 3 goes to 7, 7 goes to 8, 8 goes back to 3. That permutation has done its work. And so now we're done. So there is the word. It's not really an English word, but it's still an anagram of the word education that is the result of applying this permutation to the word education. So there is a nuts and boltsy introduction to how this stuff works. What I want to do next is to think more deeply about the concept of order. So one of the main things that I've been trying to stress is that the order of elements in a permutation group, the order of elements in a permutation group is completely determined by the cycle type of those elements. So real quickly, the cautionary tale that I have in thinking about order, and this is true in any group, right, is that order does not always behave the way that you want it to with respect to a product of elements. In particular, the order of a product can be completely unrelated, in many cases, to the product of the orders. And one of the reasons that, in general, we want this to be more related is just, I think, in part at least, because of the notation that we use for the order of elements. The order of GH is not the same thing as the order of G times the order of H. Even though we use the absolute value symbol to represent order, and the absolute value of real numbers does satisfy this multiplicativity, but don't be fooled when we're talking about order of elements in abstract algebra. The order of a product doesn't necessarily have anything to do with the product of orders. But on the other hand, there are situations where we do know how to compute the order of a product. We just need to know more about how those elements that form the product interact with one another. And so this example asks us to find a couple of elements in S4, so the symmetric group on 4 symbols. And each of those elements should have order 2, but their product needs to have a different order. I want to find an example where the order of the product is 1, an example where the order of the product is 2, and an example where the order of the product is 3. All right, so let's get started here. First of all, in S4, in the symmetric group on 4 symbols, one of the things that we can say for sure is that elements having order 2 kind of have 2 different forms. If I were to list out all the elements in S4 that have order 2, they can be, on the one hand, they can be 2 cycles, the transpositions. So I'm just going to kind of list here choices for alpha and beta that have order 2. On the one hand, we can just have single transpositions. And I'm just going to list all of them out. I mean, S4 is not a gigantic group, so we can actually just list out all the possible transpositions. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So there's 6 transpositions that I could choose from. Each of those is an element that has order 2. But there are also, in S4, products of 2 disjoint transpositions. 2 disjoint 2 cycles. And there's 3 of those. 1, 2 composed with 3, 4. There's 1, 3 composed with 2, 4. And there is 1, 4 composed with 2, 3. So in total, I can list 9 elements of S4 that are elements of order 2. There are 6 that are just individual transpositions, and there are 3 that are products of 2 disjoint transpositions. And remember, those products are going to have order 2 because, being disjoint, these transpositions that form these products of disjoint transpositions are going to commute one with another. And therefore, the order is going to be the least common multiple of the orders of those transpositions themselves. But the least common multiple of 2 with itself is going to be 2. So here I have my 9 different elements to choose from. So we can go real quickly through the examples that are being asked for here. The first example is to find elements of order 2 which have the property that their product has order 1. Well, there's only one element in any group that has order 1, and that's the identity element. So what this first question is asking me to do is to find transpositions alpha and beta such that when I compose them together, I get the identity. Well, we know that any transposition is its own inverse. And so if we were to choose alpha and beta to both be the same transposition, for example, if alpha is, say, 2, 4, and beta is 2, 4, then alpha and beta each have order 2, but alpha beta is the identity element, right? The identity permutation. And so the order is equal to 1. So that example suffices for our first question, our part A. How do I find examples of elements of order 2 whose product has order 1? Okay, so that suffices for part A. Now how do I find a product of transpositions, or a product of elements of order 2, I should say, that also itself has order 2? Well, in my list, we already have kind of some examples jumping out at us. If I take, for example, 1, 3 and 2, 4, and I compose them together, each one of them is an element of order 2. But when I compose 1, 3 with 2, 4, because they're disjoint, I get another element whose order is 2, the least common multiple of 2 with 2, because they're disjoint and therefore commute. Right? So 1, 3 and 2, 4 provide us with an example of what's being looked for in part B here, which is find me elements of order 2 whose product has order 2. Find just 2 disjoint transpositions can do that. And then finally, how do I find a product of elements of order 2 that has order 3? And this is to me the most unsettling example in this problem, because if order behaved as nicely as we wish that it did, we would at least expect that the order of a product of elements of order 2 should be 1, 2, or 4, right? It should be either a factor or a multiple of 2's. But this example shows that that's not even the case. How do I find a product of elements of order 2 that has order 3? Well, let's think about what elements in S4 have order 3. The 3 cycles, in fact, are the only examples of elements that have order 3 inside of S4. And so maybe I can find a product of elements of order 2 that's going to give me the 3 cycle 1, 2, 3. Well, we know how to do that because we know how to decompose 3 cycles into products of transpositions. I can just take alpha to be 1, 3, beta to be 1, 2. Right? The transposition 1, 3 has order 2. The transposition 1, 2 has order 2. But when I compose them, 1, 3 composed with 1, 2 is going to give me the 3 cycle 1, 2, 3, and that has order 3. So if nothing else, this quick example is just the cautionary tale to say that just because we know the order of 2 elements in a finite group does not guarantee in general that we know what the order of their product is going to be. We really do need to know how those elements interact with one another more specifically before we can say for sure what the order of that element is going to be. So let's move forward from here into thinking a little bit more broadly about orders of elements in symmetric groups. Because this gets into the conversation about cycle types that, for me at least, is one of the most important conversations that we can have about symmetric groups in general. Because one of the things that we find is that the cycle type really tells us a lot about a symmetric group. In Sn, for example, in the full symmetric group on n symbols, the cycle types, the types of cycles that make up permutations, actually form a partition of the symmetric group into what are called conjugacy classes. Conjugacy classes are ways of dividing up the elements in a group such that the elements within a common piece have a lot of the same algebraic properties. And in the case of Sn, conjugacy class is completely determined by cycle type. Conjugacy classes also form the building blocks of what we call normal subgroups of groups. Normal subgroups are going to be an obsession of ours, starting with chapters 8 and 9 of our semester. So when we get there, we might have occasion to talk more deeply about conjugacy classes because they form the building blocks of these normal subgroups, kind of the most important building block subgroups inside of a group that we can use to build the larger group. But all of that as background, as prologue, let's think about how to answer the question that's here, which is, can we figure out whether the symmetric group on 10 symbols has an element, or maybe more than one element, whose order is 24? Well, so to get started, we want to use the observation that kind of we used on this last screen, which is that if I have disjoint cycles, then the order of a product of disjoint cycles is going to be the least common multiple of the orders of the cycles themselves. So what we can do is kind of turn this question into, is there a way for me to take the least common multiple of a set of orders of cycles and have that least common multiple come out to be 24. Okay. So what I might do, even before we start thinking about permutations and cycle types and all of that more detailed stuff, what I might do if I'm in this situation is just think about number theory for a minute. Give me some examples of lists of numbers whose least common multiple is 24. And then after that, we'll start looking at whether or not those can be the orders of a cycle type that lives inside of S10. So just reminding myself that these are going to be orders of cycles at the end of the day. But let's start listing some possibilities, just thinking from a number theory perspective. Well, least common multiple of 24 with itself, of course, is going to be 24. The least common multiple of, well, if I have 12 as a part of this, I can't do 12 and 2 because 2 is already a divisor of 12, so that's not helpful. So I've got to go to a smaller factor of 24. I've got to go down to 8. And the only way to get 24 as a least common multiple of 8 with something is to take the least common multiple of 8 with 3. So least common multiple of 8 and 3 will give me 24. Remember that it's very common in a least common multiple for the numbers in my list to kind of share factors with one another, but that's what tends to create a lot of overlap. That's kind of, you know, if I'm just kind of thinking about this from the from a getting started perspective, I probably want to minimize that overlap if I can. So 8 and 3 is a way of getting 24 as a least common multiple. 6, so let's see, what would I have to include if I needed to get the least common multiple of 6 with something to be 24? So 6 is missing, it's missing a factor of 2 to get me up to 24, but the least common multiple of 6 and 4 is 12, so that's not going to quite do it. So if I want 6, I actually need to go up to 8 before the least common multiple of 6 with that thing is going to equal 24. So you kind of get the idea of what I could do. I could just list a bunch of different possibilities. But just to expedite our process, let's endeavor to list all possible cycle types in S10 and figure out whether any of them give me a least common multiple equal to 24. So listing cycle types in S10 is the same thing as listing partitions of the number 10, integer partitions. Partitions of 10. Okay. So what I'm kind of doing here is giving different ways of adding up positive integers so as to get 10. One way is just to add 10 to nothing, so that's just a trivial partition. Another way would be to add 9 plus 1. Another would be to add 8 plus 2. Or I could split that 2 into 1 plus 1. I could also take 7 and add 3. Or I could split that up into 7, 2, and 1. Or I could split it up into 7, 1, 1, and 1. I could take 6 and 4. Or I could split that 4 up into 3 and 1. I could split that 4 up into 2 and 2. I could split that 4 up into 2, 1, and 1. I could split up the 2 there into 1s, so 6, 1, 1, 1, 1. I know I'm kind of bumping into my browser window here. Let me get it out of the way. I could take 5 and add it to 5. Or I could do 5 and 4 and 1. I could do 5 and 3 and 2. I could do 5 and... you get the picture, right? 3, 1, and 1. I could do 5, 2 and 2, and 1. And I'm just going to kind of leave it there. There are a whole lot of partitions of the number 10. I think there might be 60 or something like that, different possibilities that we could list. But we only care about whether one of them is going to give me 24 as the least common multiple. So let's start to look at what the LCMs would be on this list, because the LCM is going to tell me the order of a permutation that has that cycle type. So the least common multiple of 10 with nothing else is just going to be 10. The least common multiple of 9 and 1 is 9. Of 8 and 2 is 8. So an element with this cycle type is going to have order 8. Same thing with an element of the cycle type 8, 1, 1. 7 and 3, meanwhile, are going to give me 21 as the least common multiple. 7 and 2, 14. 7, 1, and 1, 7. 6 and 4, as we discussed a minute ago, 12. 6 and 3 is going to give me 6. 6, 2, and 2 is going to give me 6. Same thing with 6, 2, 1, 1, and 6, 1, 1, 1, 1. 5 and 5 is going to give me 5, but 5 and 4 will give me 20. 5 and 3 and 2. Ooh, 5, 3, and 2 is interesting, because those are all relatively prime, so their least common multiple is the product. It's 30. 5 and 3 is going to give me 15. 5, 2, and 2 is going to give me 10. And so on and so forth. So what we're seeing right off the bat is that there's actually a pretty wide variety of different element orders inside of S10. But can we get 24 as one of them? Well, it's appearing like the answer is no, because in order for 24 to appear as a least common multiple, we really want there. We really need my cycle lengths to have at least an order of 8. Right, I need to have an 8 at the party because the only way for me to get enough powers of 2 to make 24, so think of 24 as being 2 to the power 3 times 3, right? I'm going to need to have, I can only have 1 3 somewhere in my cycle lengths, and so 3, maybe a better way to say this is I need to get a 3 from somewhere, and so I could have, maybe let's think about it this way. I need to get a 3 from somewhere, and so I either need a 3, a 6, or a 9. Okay. The problem is with 9 that 9 is not actually a divisor of 24. 3 and 6 are. So I need either a 3 or a 6 cycle to be a part of my universe here. But if I have a 3 cycle, then in order to get up to 24, I need to get 8 from somewhere else. Okay. And so I would need a 3, and I would also need an 8. But I don't have an 8 plus 3 cycle type because that would need 11 symbols to permute, and I don't have 11 symbols to permute. If I started with a 6, then the way to get the least common multiple of 24 using a 6 is I would have to, well, is that even possible? I'm not even sure that it's possible. We could do, well, no, I guess we could do 6 and an 8 or something, right? But the least common multiple of 6 with 8 would be 24, but again, I don't have 14 symbols to permute, so I can't have a cycle type of 8 plus 6. And so the answer to the question about whether S10 has an element of order 24 is the answer is no. So there's no element of S10 that has an order of 24. And for that reason, the answer to the next question, what about A10, is also no. After all, in order for a permutation in A10 to have order 24, it would have to be every even permutation of 10 symbols is also a permutation of 10 symbols. So if no element of S10, the whole group, has order 24, then certainly no element of any subgroup is going to have order 24. So the point of this exercise is, again, if you're investigating the order element, the element order properties of permutations, the way to do it is to start listing out cycle types. And the cycle type, the least common multiple of the cycle lengths, is going to determine the order exactly and uniquely. So I want to take that and move it a step further. So we've been talking about element orders up until this point, but what we haven't started talking about yet is the sign, the parity, the evenness or oddness of permutations. And so I like this proposition because this is going to give us an example of a problem where we can kind of do two things. We can think about permutations and their signs, evenness and oddness, and we can also use it as an occasion to think again about subgroups and how we think about what is it that makes a subgroup a subgroup. So real quickly, let's take a look at the statement of this proposition before we get to pull out a napkin and start trying to prove it. So here we're starting with a subgroup of the symmetric group. So symmetric group on n symbols, we don't know what the value of n is. I'm going to assume that it's at least equal to 3, so at least we have an interesting group here. And we have a subgroup of Sn. And so the claim here is that either that subgroup resides completely within the alternating subgroup, either H is completely a subgroup of An, or if it's not, then the elements are split equally among even permutations and odd permutations. So there are exactly as many even permutations in this subgroup as there are odd permutations in this subgroup. So thinking about just sketching this as a picture for a minute, so if I've got my full symmetric group Sn, maybe it looks like this. So here's my symmetric group Sn. Inside of that symmetric group, there is a alternating subgroup, so my even permutations only, An. Right? So these are my evens. And then, of course, if the evens all reside there, that means that all of my odd permutations reside outside of An and the complement of An in Sn. And so what this proposition is saying is that if I have absolutely any subgroup, let's call it H, absolutely any subgroup of Sn, that there's only two possibilities. Either the subgroup H completely lives within An, right? Or if it does not live completely within An, then it lives exactly half within An, and the other half is outside of An. So half and half. So these are my pictures, right? Either my subgroup is completely a subgroup of even permutations, or if it's not, then it has to have exactly as many odd permutations in it as even. All right, so we're charged here with proving a statement that is an OR statement. And one of the greatest things about that is that we have this law of disjunctive syllogism, if we want to call it that, that gives me a strategy for how I'm going to try to prove this. So I'm just going to kind of write down on my napkin here, disjunctive syllogism. And the form of a disjunctive syllogism is to say that if one of these conditions is not true, then the other one must be true. So let's assume that condition 1 is not true. And then we want to show that condition 2 must be. Okay. So looking at my conditions once again. Condition 1 is that every element of H resides within the alternating subgroup. So in other words, this is condition 1 is this picture. So what we're going to do is assume that this picture does not hold, and therefore we need to show that this picture must hold. So that's going to be the strategy of my proof here. So if not, then this. Okay, so there's my strategy. Let me try and get flesh out a proof of this thing on a napkin. So if 1 is false, that means that it's not true that every element of H is even. So what we can say is not every element of H is even. So that's kind of my assumption that I'm working on. And so what that does to my picture is it kind of shows that H kind of slops outside of, there's a piece of H that escapes the alternating subgroup. So let's kind of draw H like this in my assumption. And I'm going to draw it like that to suggest that there is some element, let's call it alpha. there's some permutation that is a part of H that is not an even permutation. So if 1 is false, then there exists an alpha in H, which is an odd permutation, right? And so what I want to do is use that odd permutation to argue why H must exactly be half and half. Half of the elements of H are even, and the other half of the elements of H need to be odd in that scenario. So why must that be the case? Well, one of the best ways, one of the smartest ways, I would say, to show that the elements of H are half and half is to show that for every even element of H that you give me, I can give you an odd element of H, and vice versa, that odd element of H corresponds uniquely with the even element that you gave me. In other words, what I want to do is set up a one-to-one correspondence, a bijection, between the odd elements of H and the even elements of H. So that if you give me an even element of H, I can give you an odd, and if I were to give you that odd, you could give me back the same even. One-to-one correspondence, a bijection between the even elements of H and the odd elements of H. How are we going to get that? Well, let's suppose that you give me an even element of H. Let's call it sigma. So I'm going to kind of write this down here. For any even sigma in H, my question is, how can I relate that sigma to some odd element of H in a systematic way? Right? How can I produce an odd element of H if you give me a particular even element of H? And the key, the secret sauce, is that we know H has some odd element in it. We're calling it alpha, right? Alpha is my, what do we want to call it? Alpha is my looking glass. Alpha is kind of this thing that's going to reverse the character of anything that I compose it with. Because after all, and this is the key engine of this proof, we know that if I have an odd permutation and I compose it with an even permutation, that the result is always going to be odd. Right? And vice versa. If you give me an odd permutation and compose it with an odd permutation, that result is going to be even. Right? And with that in mind, knowing now that you've given me an even permutation, sigma, I can give you an odd permutation by just multiplying composing that even permutation with an odd permutation. And I have a natural odd permutation to use. I have alpha. So for any even permutation sigma, we know that alpha times sigma is going to be odd. Alpha times sigma is odd, for sure. But why do we know that alpha times sigma is not just an odd permutation, but it's an element of H, H being the subgroup that we started this proof with? Well, that is just an artifact of closure, because H is a subgroup, and alpha and sigma are both elements of H by assumption. That means that their product is an element of H by closure, right? And so if you give me sigma, an even permutation, I can give you alpha sigma, which is an odd permutation and also belongs to H. So for every even permutation of H, we can find an odd permutation of H. Now, how do I know that it goes both ways? If you give me an odd permutation of H, how do I produce for you an even permutation? Well, maybe another way to think about it will be like this. Suppose that it goes the other way. Suppose that I have this alpha sigma over here. How do I go backwards? How do I know that this is a one-to-one correspondence? In other words, how do I know that if two people give me different even permutations and I multiply them by alpha, that I'm not going to get the same odd permutation out of this? Well, we know that because we can also go backwards. We also know that for any odd permutation, so if you start out by giving me something odd, let me draw this in a new color here. Let's say I have tau. Tau is an odd permutation. How can I produce for you an even permutation? Well, to turn something odd into something even, we just have to multiply by something odd. according to this principle down here, right? So if I multiply tau by something odd, it's going to become even. And what I want to multiply tau by is not alpha, but I actually want to multiply it by alpha inverse. Alpha inverse tau. Alpha inverse tau is going to be even. Because after all, tau is odd by assumption, alpha is odd by assumption, and we know that the inverse of a permutation has the same sign as the original permutation did. We also know that alpha inverse belongs to H. Because H is a subgroup, it has the inverse property. And therefore, if alpha belongs to H, alpha inverse belongs to H. Also, alpha is odd implies alpha inverse is odd. And the composition of alpha inverse with tau will be an even permutation, because it's odd composed with odd, and it belongs to H again by closure. And so this gives me a one-to-one correspondence going in both directions. So what we could say, the reason I wanted to use alpha inverse is that what this has done is it's set up a function for me that kind of goes back and forth between the elements, the even elements of H and the odd elements of H. So let me try and write down what this function is. Let me call it f. So this function is going to go from H intersect an to H complement an, H minus an, right? So just so we don't get confused with the notation that I'm using here, this function is going to take an even element of H and produce for me an odd element of H. Right? So it's going to be a function that goes from the left part of this, this oval over here to the right part. And the way that we decided to do this was to define this function via multiplication by alpha. So f of sigma is equal to alpha sigma, where alpha is this odd permutation that belongs to H that we produced by our contrary assumption that 1 is false, right? That there exists some element of H which is not an even permutation. Right? So f of sigma is equal to alpha sigma. And if sigma is an even permutation, then alpha sigma will be an odd permutation, because alpha is odd, and alpha sigma is therefore odd times even. And then we're claiming that f is a bijection, is one-to-one and onto. And so I suppose the last thing that we would do here, let me go back to my napkin and try and put this piece down, is let's actually do the one-to-one and onto proof here, and then I'll write it up in nice fashion. So how do we know that f is one-to-one? Well, if f of sigma is equal to f of tau, so if I have two permutations that go to the same place, that means by definition that alpha composed with sigma is equal to alpha composed with tau. But these compositions are group operations, and so we can use the left cancellation property that exists in every group, and so sigma is equal to tau. So clearly f is a one-to-one function. Why is f onto? Well, if, let's say if beta is equal to f of sigma, well, no, how do I want to say this? If beta is an odd permutation that belongs to H, then how do I know that beta is equal to alpha times, or let's say this, how do I know that beta is equal to f of some sigma? How can I solve that equation? Well, f of sigma is just alpha times sigma. And I can solve this equation by multiplying both sides by alpha inverse. Now you can see why I used alpha inverse a minute ago. Alpha inverse times beta is equal to sigma. And alpha inverse times beta, because alpha is odd, alpha inverse is odd, beta is odd by assumption, and therefore alpha inverse beta is an even permutation of H. And therefore, we know that beta is equal to f of this element which belongs to the domain of my function, right? And that shows that f is onto. The other sneaky little shortcut that we could have used, and let me just get this preserved for the record because this is a super useful statement. Since H is a finite set, after all of my permutation groups on finite number of symbols are finite groups. Therefore, any of their subsets will be a finite set. So H is a finite set, and we know, therefore, that f is a function on finite sets. And for any function on finite sets, cannot be one of these properties and not the other. So in other words, it's enough just for us to show that f is 1-to-1, because every function on finite sets is either both 1-to-1 and onto, or it's neither 1-to-1 nor onto. Right? So as soon as we show that f is 1-to-1, that will guarantee that it's also onto as well. So I've kind of gone through this really quickly. Let's take a few steps back and actually write this up as a proof, and try and make it as nice of a proof as we can, following our best practices for how to write meaningful proofs that are readable. So the first thing I want to do is to introduce the reader to my strategy. Right? So we'll use the law of disjunctive syllogism. So I just want to write that at the outset of my proof, just to signal to the reader that what we're going to do here is assume that it's not the case. Assume that it's not true that every element of H is even. Right? So that's, we will prove that then exactly half of the elements of H are even. Give me just 1 second before we get started on this proof. I am. I'm sorry. Is this something you could drop me an email about for today? Because after I'm done with this, I have to leave campus. So let me give you my contact info. Just don't drop me an email today. I'll get to it right away. Okay, so this is telling the reader what the law of disjunctive syllogism is going to do. We're going to make an assumption that the first condition does not hold, and then prove that the second condition must hold. So since we're assuming that it's not true that every element is even, we're going to bring into being this element alpha. Okay. So by our assumption, there exists an element alpha in H, which is odd, which is an odd permutation. Right? So that alpha is crucial to the success of our proof, because it is how we sort of cross over to the other side of the looking glass, right? It's how we go from an even permutation to an odd permutation, and its inverse is how we go backwards. Right? So now, define a function. And that's this function up here at the top of the screen. A function is going to turn all of my even permutations into odd permutations. And so I'll say what it is. The function we're calling f, and it goes from the even elements of H to the odd elements of H. And f of sigma is equal to alpha sigma. Okay. So here we define this function. And if we hadn't walked through our thought process on the napkin before writing this down, this would look mind-boggling to a reader of this proof. But now we understand what this notation is saying. It's saying that we're defining a way to turn every even permutation in this subgroup into odd permutation in this subgroup. And that way will also turn every odd permutation back into an even permutation in a 1-to-1 correspondence that will prove why exactly half the elements are even and the other half are odd, because for every even, there's one and only one odd, and vice versa. Okay, so we define this function. We will show that f is a bijection between the even permutations in H and the odd permutations in H. So there I've kind of, again, shifted my burden of proof a little bit. This is how we're going to demonstrate to the reader that there are exactly as many even elements as there are odd elements. So the function f is 1-to-1, since if f of sigma is equal to f of tau, then alpha sigma is equal to alpha tau, by definition of my function. So I'll say here, by definition of f, we have alpha sigma is equal to alpha tau. But then if alpha sigma was equal to alpha tau, we can cancel those alphas, as we did right here on our napkin. And so sigma equals tau by cancellation. Left cancellation, if you like. It's the only one that we would need in that case, right? So now that we've shown f is a 1-to-1 function, now we can make the argument about finite sets. I'm going to take this cheating way out here. Since H is a finite set, and hence so are the domain and range of f, the fact that f is 1-to-1 also guarantees that f is onto. Thus, f is a bijection as desired. And so there's my proof. Sorry, it doesn't quite fit on one screen with the proposition anymore, but here it is. Right? So just one more time to follow through what this proof is doing. We're using a disjunctive syllogism to say that if it's not true that H is completely inside of AN, then it must be exactly half inside of AN. Okay? So we start by assuming that it's not completely within AN. That means that there exists an odd permutation called alpha that is a part of this subgroup. And then we define a function that multiplies any permutation, any even permutation in AN, in H, multiplies that permutation by alpha. And it therefore turns it odd. I guess the one thing I didn't write down in our proof here, and so why don't I add this in here? The function f turns even permutations odd, since if sigma is an even permutation, then alpha sigma is a composition of odd with even, which is an odd permutation. So this justifies why we can say that the domain of f is all the even permutations in H, and the codomain is all the odd permutations in H. So this will wrap up this proof. The last proof that I want to look at, and this is only going to take us a couple minutes, which is good because I have to wrap up today's stream, this is also kind of a throwback to a definition from an earlier chapter, and it's the definition of center. So I want to close just by proving that in fact the center of any symmetric group, any interesting symmetric group for sure, where n is greater than or equal to 3, that the center is trivial. So to do this, we just really need to unpack the definition of what the center of a group is. And somehow I've misplaced my my pencil. I don't know where it just went to. All right, well then, to finish the stream, instead of writing stuff down, let's just, well, here we go. I'll just use this as a stylus. So I want to show why the center of the group, Sn, is trivial. So ZSn is trivial. And this is going to be nothing more than an exercise in remembering what the definition of the center of a group is. The center of a group consists of those elements of my group, so I'm going to call them, X. So those elements of my group Sn that commute with everything in my group, such that for all sigma in Sn, we have X sigma equals sigma X. So what we're trying to prove here, another way of sort of restating what my burden of proof is. In other words, in order to, I guess what we can do to prove this, we can rule out the possibility that any non-identity permutation commutes with every element of Sn. So that's an English restatement of this proposition that we're trying to prove. So the way that I would approach this proof is as follows. So if you give me a permutation that's not the identity, so give me an alpha not equal to the identity permutation, and then I'll tell you, I'll find for you an example of a sigma that does not commute with alpha. Sigma alpha not equal to alpha sigma. Right? And this should be sufficient, right? Because this would guarantee that any element which is outside of the trivial subgroup, any element which is not the identity permutation, cannot belong to the center. Because if it did belong to the center, it would have to commute with everything, and just showing that there's one thing that it doesn't commute with is sufficient to show that it doesn't commute with everything, after all. So let me just do a quick example. Suppose that you give me the permutation, something very simple. Let's say you give me 2, 5. And let's say this belongs to S5 or something like that, right? So let's suppose this is the alpha that you give me. How can I find something that 2, 5 doesn't commute with? Well, we know for sure that disjoint permutations that act on disjoint subsets of our symbols, those do commute with one another. And so if I'm looking for something that doesn't commute with alpha, I should find another permutation that is not disjoint with alpha. So my sigma needs to overlap with alpha. But also, I don't want sigma to equal alpha, because every element commutes with itself. And I also don't want it to equal any power of alpha, because all the powers of alpha commute with one another. Right? That includes the inverse, so I also don't want it to be the inverse of alpha. Right? So I think best way to do this is just to, for example, take sigma to be a transposition, and let's make it a transposition that just takes one of my symbols that's already a part of alpha, let's say 2, and transposes it with a symbol that's not a part of alpha, let's say 2, 3. Right? Then we can compute sigma alpha and alpha sigma. If I do sigma alpha, for example, alpha is going to act first, and alpha does 2 goes to position 5, and then sigma is going to act, and 5 doesn't go anywhere, so 2 goes to 5. So this is 2, 5, sigma alpha is 2, 3, 2, 5. I'm going to skip the calculation here. That's 2, 5, 3. This ends up being 2, 3, 5. And we can see those are different 3 cycles. They're different permutations from one another. One of them happens to be the other's inverse, but that's okay. Right? And so we can write a proof of this probably by generalizing this idea, right? That if you give me a permutation that's not trivial, then it means that some element, some position is getting moved to some other position. Right? And I can then take the transposition, take as a transposition one that just flip-flops the position of one of those things with a position that's not being used. So here's, I guess, how I would generalize this, is if alpha sends position I to position K, let's say, right, then I want beta to be the transposition of I with J. And we can show then that those don't commute. Okay. So let's just write up this proof, and then we'll be all done for the day. So let's let alpha in Sn be a non-trivial permutation, we will show that alpha does not belong to the center of Sn. Right? So that's how we're doing this. If I have any non-trivial permutation, it can't belong to the center, and therefore the only thing in the center is the identity. All right, so how do we do it? Since alpha is not equal to the identity, there is an I and a j such that alpha of I is equal to j, where I is different from j. So it's moving some position I to a different position j. Right? That was the first piece of the argument. In our specific example, I and j were 2 and 5. So alpha is moving position 2 to position 5. Right? Now let k be different from I and j. This is possible only because we have at least 3 positions to work with. Only because n is greater than or equal to 3. Right? So we have at least 3 positions to work with. So if A is moving one of them to another one of them, there's still one more position that I can choose from that's different from the other 2. Right? And now what we claim is that sigma equals the transposition of I with k does not commute with alpha. And to figure out why sigma doesn't commute with alpha, let's just check and see what sigma does to position, what sigma alpha and alpha sigma do to just the ith position. So to prove this, we'll show that sigma alpha and alpha sigma send the ith position to different places. Okay, so there's, again, shifting my burden of proof. Right? So let's check how sigma alpha acts on the ith position. So alpha is going to act first, again, reading my permutations from right to left. And when alpha acts first, it sends position I to position j. Right? That's what this sentence up here says. So that's going to equal sigma of j. Right? But on the other hand, sigma is a transposition of I with k. J is not changing under that permutation. And so that's just going to equal j. Sigma alpha applied to I is going to send position I to position j. On the other hand, alpha sigma applied to I, well, here, in the permutation alpha sigma, sigma is going to act first this time. And when sigma acts first, I is getting sent to position k. And so this is going to be alpha of k at the end of the day. But what does alpha do to position k? Well, k is different from I and j. We don't know what actually ends up happening in that position. But let's see. So how do we finish this argument? Actually, I think I might have run into a little snag here. We may have a little bit more to iron out than I'm giving this piece credit for. How do we know that this is not equal to j? Is it possible that alpha could send j to position k? I don't know that this is what we want. So I think maybe what we wanted to do is look at, maybe we wanted to start by feeding alpha position k? No. Maybe feeding alpha position j? Well, wait a minute. No, we're fine. We're fine. Okay, so I'm thinking on my feet here. How do I know that alpha of k cannot be equal to j? I know alpha of k cannot equal j, so I'm going to put a not equal to here just to not get us confused. Not equal to j. And I know that's the case because alpha of I is equal to j. So alpha is sending I to j. And it can't send more than one thing to the same position. A permutation is always a bijection, right? It's always one-to-one. So I can't send two positions under the same permutation to the same image. I can't send them both to the same spot because alpha of I is equal to j, and alpha is one-to-one, as are all permutations. And so that actually completes my proof. Alpha is a one-to-one function because it's a permutation. Therefore, because we know alpha sends I to j, alpha cannot send k to j. And therefore, sigma alpha and alpha sigma are different permutations because they send position I to different spots. And that concludes our proof. So the center of any interesting symmetric group is always trivial. There's no permutation that commutes with every other permutation if I have three or more symbols, other than the identity permutation. That's going to wrap up today's live stream. I hope that these problems were helpful. And those of you who are my students, I'll see you for your quiz tomorrow morning.